Yeah, I'd like to thank you guys for organizing this conference. It's an honor to be invited to attend and to speak at the conference. Secondly, many years ago, when I just arrived in Columbus, I got a very kind message from you guys inviting me to come to another exhibit. So I came to another, and also I got a bit surprised because I didn't know that my talk was supposed to be for 2 hours. So, but I understand that at this conference we have a big before. Yes. Okay. So let me begin my talk by recalling some notion from geometry that I know very little about. Okay. So so let X be a Taylor manifold. So it means that X has three structures: a complex structure, a Riemannian structure, and a simplified structure, which are compartments in some sense. And suppose that you have a subgroup of automorphism of X, and suppose that it is compact. Then in 1987, Gangxian and also Gangxian and Yao define the anti-invariant. So the anti-invariant alpha factory of X. And I won't be able to say what it is. I just want to say that so this one application of this invariant. So suppose that X is a Fano variety. Okay, so can I give you an example of the Taylor manifold or Fano variety? So the basic example is going to be X is just a quantum space where V is an dimensional space over C. So that would be our basic example, and this is the only one that we are going to consider. So Jian showed that if X is a Fano variety, and suppose that the invariant is X the dimension of X divided by the dimension of X plus 1, then we can show that then in this case X admits a G invariant Taylor-Einstein list. So it was very important result in geometry. It turns out that this anti-invariant is also of interest to the analytic geometers. So so let me just mention one result. In the one into the my and polar. So they show that if your G is finite and X is Fano like before, then this alpha factory of X is also equal to something that is LCD I3. So this is so-called the log canonical threshold. Okay. So, well, in fact, in 1981, Thomson proved the following theorem. So he proved that
Is that J?
yes, JGP. That for in the end, for infinite, such G of G and C. So he proved that the anti-invariant of the G acting on this on EN minus 1 is only bounded by 4 times n. Of course, the question is how could John work on something that wasn't defined? Well, there's a connection to the representation theory. vector space. And okay, so X is going to be B. So if G is a finite subgroup of G and G, then we say that G has a semi-invariant of K on B if when you look at the G model, the K symmetric power of B, so this is going to be having a one-dimensional submodel. So if the model is Euclidean, then what you get is just a invariant. And then let us define the D of G to be the minimum on the K such that the G has a semi-invariant K. Now it's easy to see that the D of G exists because it's very bounded by the order G, which is finite. And then, so the connection between the representative theory and this invariant was shown by, was observed by, in a paper by Vanya-Chekhov and Ustia-Schramm in 2009. So they observed that the alpha invariant of this space is going to be bounded by the D of G divided by N. So in fact, the result that the Jodosa proved was that the D of G is bounded by full N squared. Okay, and then divided by N, then we get what did. So, okay. So in the same paper, John Thompson created the following conjecture. That in fact the anti-invariant should be bounded universally, not depending on your N. So there should be an absolute constant C such that for N, for finite, such that G will be and C, then what we have is we have the alpha invariant is bounded by C and BG is bounded by 4 times N. Okay. So the first major result that I want to talk about today is that Thompson conjecture some C, and the C that I will take is value something like maybe 1,184,036. Okay. Well, maybe, yeah, right. Okay. So, let me make a note that of course, I mean, you can see that well, this is probably inflated. So what would be the real C? Well, I don't know, but we can show that this C cannot be smaller than 6, because if you look at the example of SN25 inside GN2C, then you see that the G is only 12. So 6 should be the smallest one, but maybe it doesn't do it for the conjecture. Okay. Right. So now let me talk about some of the main ideas behind the proof of this theorem. So let me begin by telling you how John Thompson proved this theorem. So the proof is really very short, it's just one page, maybe less than one page. And the main idea is to, instead of working with the atomic spin, we should go to the field of quantum characteristic. Okay. So how that doesn't divide to the root order, and don't show that we can assume that your G is irreducible and also primitive on B. Now, instead of this complex space, what you can do is we have to replace our B by F to the end where F is a closed field and the basis of your F is going to be P. So now we are going to look at the R, the ring of a polynomial in n level. Okay. So inside the ring we have the R sub B. What is R sub B? R sub B is the subspace of homogeneous polynomial of degree B. I also want to look at the J. What is the J? J is the ideal of R generated by all the P powers. So F to the P, where your F is in R and F at 0 is 0. Okay. So it's easy to see that your J is going to be spanned by all the monomial like x1 to the e1, xn to the en, where the max of the ei is at this P. So now if I look at the R sub P minus 1 times n, then we can see that this is going to be just the intersection of this with J, and then I have a one-dimensional complement, which is spanned by the x1 to the P minus 1, xn to the P minus 1. It's not a submodel, but it's just a complement like a subspace. But the point is that shows that the R has a submodel of 2-dimensional 1. And therefore, if you look at the base image power, then the scene P minus 1 and N W B and the submodel of dimension 1 by dualizing. Okay, and this is what you want. Okay, so the point is, so what is the P to choose? So what is the P to choose? Well, so John said that what you do is, so you can use the Bertrand postulate. So it says that there is some P, right? P between 2n plus 1 and 4n plus 2. Okay. And then there's a theorem to find John Thomson, not the orthogonal one. It says that, so under the assumption that your G is reducible and primitive, and for this kind of P, then what you can show is that your G is actually the direct product of the OP of the center of G with some G naught, where P doesn't divide the order of G naught. Okay. So now what you do is you just apply this argument. So we apply the argument to your G naught, because your P is equivalent to the order of G naught. Then you see that the D of G naught is going to be bounded by P minus 1 times n. And D of G naught is just the D of G. And this is going to be, well, at most 4n plus 1, so it's going to be 4n squared. So this is the root table of 0. So in fact, this proof is going to be the first step of our proof of the main resolve. Okay. So how do you show that you have some semi-invariant? Well, okay, so we look at the symmetric power, k-symmetric power. Maybe you know the character of that, there is a formula for that, and then you try to show that there is a linear transition of that complex character. But the problem is, it's not easy to compute this k-symmetric power of any character. So for instance, if you try to do this computation with gap, then I think that you cannot go up to sim 40. It's already gap already made up. So how do you work with the sim k? What can you current? Okay. So here's the key character estimate. So before we go to proposition 1. Okay. So let's try meaning a new character for some group G, and suppose that there is some constant gamma between 0 and 1, such that for all the non-functional elements in G, we know that chi of x is bounded by gamma and half 1. Okay. Then for any non-functional element G, for any k, what you can prove is the following. You can show that the sim k of chi evaluated at G is can be bounded by the product of gamma n plus j divided by gamma and j 1 from 0 to n minus 1 divided by gamma total. And what is the n? N is just the degree of chi. Right. So in particular, we know if you choose your n to be 3k divided by gamma to the 1.5, then we know that this sim k is then bounded by gamma to the k over 2 and the degree of this decimal power. Okay. And I think I also need another estimate. So suppose that if your gamma can be chosen to be 1 divided by root of 2, then I can put some estimate like this, but instead of that, I will have a Cn. It's very bounded by something like 8, 7, and 27 over 32 to the n over 2. It's important is something smaller than 1. And sim n, chi, and 1. Okay. So now given this proposition, I can give you a criterion. So how do I produce a semi-invariant? Given the assumption of proposition 1, and suppose that, okay, so I'm going to take this, and is at least 3 times k and gamma to the 1.5. And the second condition is the order G, or the center G, is at most gamma to the negative k over 2. And the first condition is the order of center G intersecting G prime divide k. Then you can show that you have a semi-invariant k. So then you can show that sim k of chi contain a linear sequence. 1. So the proof is really easy. So first you use the fact that so first I look at the chi and I restrict to the center G. So by Schur lemma, this is going to be n times some lambda, where lambda is a linear character in the center. Then this condition, the third condition implies that when lambda to the k distribution at the center intersecting with G prime, And therefore, lambda to the k is a character of a function of center by this G prime. G is just center G, which is isomorphic to G prime mod G prime, which is a subgroup of G mod G prime. But G mod G prime is an Abelian group, so we can extend the lambda to the k. So lambda to the k extends to a linear character, say mu of G. Okay. So I want to show this mu is going to be occurring in this asymmetric power. And then what you do is you just compute the inner product. Okay. Well, this is going to be just a sum of the sim k pi G mu bar G, and I'm going to break it into two pieces. The one over the central element and the one outside. Okay, then this is a non-negative number, so I can say, I should put D and D is not to D. Okay, and then I replace it by the absolute value, and then this is going to be at least the absolute value of the first thing here. But you can easily see this because the mu is just the recession of lambda to the k. So it means that this is just the order of t times sim k. On the other hand, for this part, because your G is not centered, then I can apply the this estimate here. So it's going to be, so I get the gamma to the k minus 2 over G minus C and sim k times 1. Okay, so then you get this to be larger than sim k by 1 times over G 1 minus gamma to the k over G mod Z. Okay, and then because of this condition, you know this is not negative, and therefore no is positive, and therefore you get a linear transition in the case with power. Okay. Right. So how do you prove the theorem of the length theorem now, which is right here? So I should say that this is a post-classification theorem. It means that it depends on the classification, and so we have to listen on the secret group to work with, and not only that, but also we have the theorem, or maybe rather the product of a Finite strata and length plot. How can you approach a maximal subgroup? Whatever overlap, find a linear group or some other group. Okay, so so I will say using the Algebras and stuff, I will say theorem. We can reduce the rule of the theorem A, the main theorem A, to proving the following theorem. So theorem 3. Okay. And now I can explain to you where did this C come from. Right. So there is a constant B which can be taken to be 592,000. Such that the following. So for any finite G inside C, and I'm going to assume that your G is irreducible, primitive, tensor decomposable, and not tensor induced. So as you can see, I am trying to exclude all the C1, C2, C3, and so on classes in the Algebras presentation. Then one of the following occurs. Okay. So the first one is for any prime P greater than D, then we know that the seam P minus 1 and V, so V is actually the C to the N here.